Hello and welcome. You are watching Afeez Azeez Geospatial Academy, a learning platform where you will discover everything about the fascinating field of surveying and geoinformatics. Welcome to our new series titled Geospatial Science Explained, a brand new series. In the series, we will dive in deeper into the world of surveying and geospatial science as it relates to our daily activities. Today, we are talking about Episode 9, Global Navigation Satellite Systems GNSS Introduction. Imagine standing anywhere on Earth. Whether you are in a remote desert, a dense rainforest, the middle of an ocean, or a busy city, your smartphone can determine your location within seconds. Have you ever wondered how this is possible? How can a device in your pocket accurately determine its position on a planet that is more than 12,000 kilometers in diameter? How do aircraft navigate across continents? How do ships cross oceans? How do surveyors establish property boundaries with centimeter-level accuracy? How do ride-sharing applications locate passengers and drivers in real time? The answer lies in one of the greatest technological achievements of modern civilization: Global Navigation Satellite Systems, commonly known as GNS. Welcome to Geospatial Science Explained. In this episode, we will explore the principles, history, components, operation, applications, errors, correction methods, and future of GNS technology. By the end of this lesson, you will understand how satellite positioning works and why GNS has become one of the most important technologies in surveying, GIS, remote sensing, engineering, transportation, and everyday life. Chapter 1. What is GNSS? GNSS stands for Global Navigation Satellite System. It refers to a constellation of satellites orbiting the Earth that provide positioning, navigation, and timing information to users anywhere on the planet. GNSS enables users to determine position, velocity, direction. Time, simply put, GNSS tells us where we are, how fast we are moving, and the precise time. Unlike traditional navigation methods that relied on landmarks, compasses, or celestial observations, GNSS provides continuous and highly accurate positioning worldwide. Today, billions of devices depend on GNSS. Before we continue, please remember to subscribe to this channel, like this video, share it, and drop a comment below. Your support helps us grow this academy. From smartphones and vehicles to aircraft, ships, and surveying instruments, GNSS has become an essential part of modern life. Chapter 2. The History of Satellite Navigation. The story of GNSS began during the Cold War era. In 1957, the Soviet Union launched Sputnik 1, the world's first artificial satellite. Scientists observed that the frequency of Sputnik's radio signals changed as the satellite moved. This phenomenon, known as the Doppler effect, demonstrated that satellite signals could be used to determine position. The success of these experiments inspired the development of satellite navigation systems. In the 1970s, the United States Department of Defense initiated the Navstar GPS program. GPS became fully operational in the 1990s and revolutionized global positioning. Other nations later developed their own systems, creating today's multi-constellation GNSS environment. Chapter 3. The major GNSS constellations. Several GNSS systems operate today. Together, they provide global positioning coverage. The major systems include GPS, the global positioning system developed and operated by the United States. GPS was the first fully operational global satellite navigation system. Today, it remains one of the most widely used systems in the world. GLONASS Global Navigation Satellite System. Developed and operated by Russia, GLONASS provides global coverage and serves as an alternative to GPS. Galileo. Developed by the European Union. Galileo was designed as a civilian-controlled navigation system. It provides high-precision positioning services worldwide. BeiDou. Developed by China. BeiDou evolved from a regional system into a fully operational global navigation network. Regional systems. Several countries operate regional navigation systems. Examples include India's Navic, Japan's QSS. These systems enhance positioning performance in specific regions. Chapter 4. The three segments of GNSS. Every GNSS system consists of three major components. These are the space segment, the control segment, the user segment. Together they form the complete satellite navigation infrastructure. Chapter 5. The space segment. The space segment consists of satellites orbiting the Earth. These satellites continuously transmit signals containing satellite identification, orbital information, precise timing information. Modern GNSS constellations consist of dozens of satellites. These satellites orbit approximately 20,000 kilometers above the Earth. Their carefully designed orbital configurations ensure that multiple satellites are visible from almost any location on Earth at any time. Chapter 6. The Control Segment. The control segment consists of ground-based monitoring and control stations. Its responsibilities include tracking satellites, monitoring satellite health, updating satellite orbits, synchronizing satellite clocks, uploading correction data. Control stations ensure that satellite information remains accurate and reliable. Without continuous monitoring, positioning accuracy would deteriorate rapidly. Chapter 7. The User Segment. The user segment consists of GNSS receivers. Examples include smartphones, vehicle navigation systems, aircraft navigation equipment, marine navigation systems, survey-grade GNSS receivers, agricultural guidance systems. These receivers collect signals from satellites and calculate position. The receiver is the component most people interact with daily. Chapter 8. How GNSS determines position. One of the most fascinating aspects of GNSS is how it calculates position. The process begins when satellites transmit signals. Each signal contains the exact time at which it was transmitted. The receiver compares this transmission time with the time of reception. Because radio signals travel at the speed of light, the travel time allows the receiver to estimate the distance to each satellite. This estimated distance is known as a pseudorange. By measuring distances to multiple satellites, the receiver determines its location. This process is called trilateration. Chapter 9. Understanding trilateration. Trilateration is the mathematical technique used to determine position. Imagine standing somewhere within a large field. If you know your exact distance from one known point, your possible location lies somewhere on a circle. If you know your distance from a second point, your location narrows. Adding a third point further refines your position. GNSS works similarly, but in 3 dimensions. The receiver calculates distances from multiple satellites. The intersection of these distances reveals the receiver's position. To solve for latitude, longitude, elevation, and receiver clock error, signals from at least 4 satellites are required. Chapter 10. Satellite Signals. GNSS satellites continuously broadcast radio signals. These signals contain satellite coordinates, orbital information, precise timing information, health status. Receivers decode this information to compute positions. Signal transmission and reception occur continuously and automatically. This enables real-time navigation and positioning. Chapter 11. Positioning Methods. Different GNSS applications require different levels of accuracy. Several positioning techniques are available. Autonomous positioning, also called standalone positioning, uses signals directly from satellites. Accuracy typically ranges from 3 to 10 meters, suitable for everyday navigation. Differential GNSS, often called DGNS, uses correction information from a known reference station, improves accuracy significantly. Real-time kinematic positioning, known as RTK, provides centimeter level accuracy. Widely used in surveying and engineering, RTK relies on communication between a base station and rover receiver. Precise point positioning, known as PPP, uses advanced satellite corrections, can achieve high accuracy without a nearby base station. PPP is becoming increasingly important in global positioning applications. Chapter 12. Sources of GNSS error. GNSS measurements are affected by various errors. Understanding these errors is critical. Major sources include satellite clock errors, orbital errors, atmospheric delays, multipath effects, receiver noise, satellite geometry. These factors influence positioning accuracy. Modern receivers and correction systems are designed to minimize their effects. Chapter 13. The ionosphere and troposphere. Satellite signals must pass through the Earth's atmosphere. The ionosphere contains charged particles that slow GNSS signals. The troposphere contains water vapor and atmospheric gases that also affect signal propagation. These delays introduce positioning errors. Advanced correction models help compensate for atmospheric effects. Before we continue, please remember to subscribe to this channel, like this video, share it, and drop a comment below. Your support helps us grow this academy. Chapter 14. Multipath error. Multipath occurs when GNSS signals reflect from nearby surfaces. Examples include buildings, metal structures, water bodies, rock formations. The receiver may receive both direct and reflected signals. This can lead to inaccurate distance measurements. Multipath is a significant challenge in urban environments. Chapter 15. Satellite geometry. The arrangement of satellites in the sky affects positioning accuracy. This concept is known as satellite geometry. Good geometry occurs when satellites are widely distributed across the sky. Poor geometry occurs when satellites are clustered together. The quality of satellite geometry is often measured using dilution of precision, commonly called DOP. Lower DOP values generally indicate better positioning accuracy. Chapter 16. GNSS in Land Surveying. GNSS has transformed the surveying profession. Applications include geodetic control surveys, boundary surveys, engineering surveys, construction layout, topographic mapping, hydrographic surveys. Modern surveyors routinely achieve centimeter-level accuracy using GNSS technologies. What once required weeks of fieldwork can now be accomplished in hours. Chapter 17. GNSS in GIS and Remote Sensing. GIS professionals use GNSS for data collection, asset mapping, field verification, spatial data updating. Remote sensing applications depend on GNSS for satellite orbit determination, image georeferencing, sensor positioning, ground control surveys. GNSS ensures that spatial data align accurately within geospatial databases. Chapter 18. GNSS in Everyday Life. Most people use GNSS without realizing it. Examples include smartphone navigation, ride-sharing services, food delivery applications, fleet management, agricultural guidance systems, fitness trackers, emergency response systems, aviation navigation, maritime navigation. Modern society has become heavily dependent on GNSS technology. Chapter 19. The future of GNSS. The future of GNSS is exciting. Emerging developments include multi-constellation positioning, multi-frequency receivers, artificial intelligence integration, autonomous vehicles, smart cities, Internet of Things applications, advanced satellite augmentation systems, real-time global corrections. These innovations will improve positioning accuracy, reliability, and availability worldwide. Chapter 20. GNSS and the Geospatial Future. As geospatial technologies continue to evolve, GNSS will remain a cornerstone of modern positioning, combined with GIS remote sensing, drone mapping, artificial intelligence, cloud computing, digital twins. GNSS will help drive the next generation of geospatial innovation. The ability to determine precise location anywhere on Earth is transforming industries and reshaping how humanity interacts with space and place. Conclusion. Global navigation satellite systems represent one of the most remarkable technological achievements in human history. Through a network of satellites, ground stations, and receivers, GNSS enables precise positioning anywhere on Earth. It supports navigation, surveying, mapping, transportation, disaster management, scientific research, and countless everyday applications. From GPS and GLONASS to Galileo and Beidou, GNSS has become the invisible infrastructure that powers modern society. Understanding GNSS is therefore essential for every geospatial professional. It is the technology that allows us to know where we are going, and how we relate to the world around us. Thank you for joining this episode of Geospatial Science Explained. In our next lesson, we will explore GNSS surveying techniques, including static surveys, differential GNSS, RTK, network RTK, and precise point positioning, and learn how surveyors achieve centimeter-level positioning accuracy.